All right. So I owe you a quiz back, and I owe you the test. I'll get them both back on Tuesday. I don't have it yet, but Tuesday. Oh, I'll have it on Thursday. Yeah, thank you. It'll be posted by this weekend sometime, but I guess, yeah, you're right. We don't have, yeah, good reminder. No class, no school on Tuesday. It's like refresh and something day. It used to be Success Day, which was a really cool thing, but they canceled it. Not enough people went to the lectures and stuff. Hmm. All right, so let me just get into new material today. So there's one thing I want to say before we get into three-dimensional stuff. And the general topic is called equipolar systems. All right, spell that. 2 L's. Yes. Equipolar systems. And equipolar systems are systems with different loads but the same behavior. And it turns out that with rigid bodies, there are a lot of times that replacing one set of loads with another set of loads makes your calculations easier. And so with rigid bodies, you can always replace a set of loads with an equipolar set of loads. So some examples of this are well, the first one is one that we already have been using. I didn't call it an equipolar system, but it's the same. That's what it is. You can replace a force couple with a pure moment. We do that all the time, but two forces that are applied that are equal and opposite are not a moment. It's two forces. We replace it with the pure moment because it makes the calculations easier. Another thing that you can do that we haven't done, and I'm not going to talk about how to do it, but you can do this. You can replace any combination of loads with a force vector at a chosen location that you choose. So a single force vector at a location of your choice and a couple. I don't find that to be usually super useful. It doesn't come up in any calculations really that I do. There was one kind of calculation that I used to do with my work a long time ago where this was a useful thing, and that is that any muscle forces for any joint can be replaced by just a pure joint moment. So a moment like a couple on one body and an equal and opposite couple on the other one. You wouldn't think so, but you can figure that out with this approach. And then the third one is the one I'm going to talk about. You can move any force vector along its line of action. Okay, so this is the one I'm going to talk about for a second. And so what that says is if you have some object and there's a force vector acting on it there, okay? The line of action, and actually I'm going to move this a little bit. The line of action is the line that is parallel to that vector and goes through the point where the force is applied. I think this picture gets that idea across better than words. Okay, so the red is called the line of action. And if it makes the calculation easier, you can move that force vector. Let me name it. So this force vector F anywhere you want along that dotted line. So you can say that that force is applied here or here or here. And this is sort of a weird thing, but you can even say that this force is applied to this object here, outside of where the object is a mile away, as long as you stay on that line of action. It's just a mathematical thing, but the math everything will be the same no matter where you move it. And sometimes that makes things a little easier. Let's see. Yeah. So let me just show you an example of this. Yes.
Like how in physics, our professor would always have normal force from the center of mass.
Yeah.
But you do it at the center of mass.
Yeah.
Is that?
Well, let's see. Is that physics people don't do a lot of rigid body calculations so they tend to think of, they're more likely to think of everything as a particle, you know, because that's sort of the kind of calculations that they've done their research more and stuff. I think that's why. And so they kind of tend to think of everything as happening at the center of mass of an object. But when you're doing rigid body stuff, where a force acts actually is important. You know, so I think that's really more what that is. Physics people just tend to think of objects as particles more than mechanical engineers and stuff do. Okay, so let me show you how this works. Oh, by the way, I said that this only works with rigid bodies. This doesn't work with deformable bodies. So if you're not considering an object as rigid, then you can't make this substitution. Let me show you give you sort of an idea of why that is. Doesn't work with deformable bodies. Deformable. So say that you have an object. So you start with this blob of, silly putty. If you apply a force to it up here, it would do that. If you move that force along its line of action, it would do this. Yeah, so you can only make this substitution and have the calculations be the same when you're treating things as rigid bodies. These are not the same. Yes?
Well, like if the line of action is more of like, what's it called, decant of a circle or
Tangent?
not tangent, but like more like barely on the object,
Yeah.
you know what I mean? Would it create different moments on the object depending on what I'm on? I mean, even about
Well, actually, that's exactly why it does work for rigid bodies, is because because the moments are the same. So it's exactly, if you think of a moment, so we do it with cross products, but if you think of a moment as like a force times its perpendicular moment arm, the idea of this is that you keep all the moment arms the same. So that's why it does work. Okay, so let me do an example. So let's say there's this guy exercising. I've never seen anyone do this kind of exercise, but it could be, I don't know. I'm not a big exerciser. And this is against the wall. Yeah. Okay. Or this is a really painful, difficult, unnecessarily difficult way to paint the wall. Okay, so let's say that we know that there's a friction contact down here. And let's say that the center of mass is 0.5 meters from where the feet make contact horizontally. So here's the center of mass. By the way, treating gravity, we'll get into distributed loads pretty soon, but treating weight like it acts at a single point at your center of mass is an equipolar system. Gravity doesn't really just doesn't calculate where your center of mass is and apply a force there. What it does is it applies a little force all over your body, and calculating the center of mass and applying the whole thing like it acts at the center of mass is just an equipolar system. Okay. Okay, so this distance is 0.5 meters. And then this distance, where the roller is 0.8 meters. And we want to know what are the reactions. Well, if you draw a free body diagram, okay, so there's the outline. The weight acts here. Did I give his weight? 80, it's supposed to be a mass of 80 kilograms. So 80 times 9.81 is 784.8. Is that right? 78. I think that's right. And then here we have a reaction force RA, and then here at the roller we have a force RB with a known direction. And notice that with the dimensions that I gave, we know the horizontal distance between these two, but I didn't give a height of the center of mass. Okay. And we know the vertical distance between the floor and the RB, but I didn't give a horizontal distance for when that force is applied. So really, like, if we're using the definition of the row vector, we can't calculate those row vectors. You know what I mean? We don't have a vertical component for this one, and we don't have a horizontal component for this. But thinking about it in terms of moving them along their line of action, you realize that those wouldn't come into it anyways. So we can move this weight force along its line of action down to the ground. And we can move this horizontal force over here horizontally until it's, you know, right above that, and it won't change anything. Okay. So here we don't know the height. And here we don't know the horizontal position. So let's fill out a table for row, force, moment. So first for the force RA, and I'm going to make this the about point. It's acting at the about point, so the row vector is 0. The force is RAX, RAY, so the moment is 0. And now I'll go to the weight force. Okay, so the horizontal component of the row vector is positive 0.5. The vertical component we don't know, but we know that it's not going to matter because this is the line of action. Okay, so I'm just going to put that in as 0. We know it won't hurt anything. The force vector is 0, negative 784.8. And multiply those two together and you get negative 39.24. 392.4. And then this one, that's the line of action of this RB. we know the vertical component is positive 0.8. We don't know the horizontal component, but that can be anything. So I'll just make it 0. And then the force vector is negative RB 0. And so you get 0.8 RB. And you can go through the calculations. You get that R is equal to 490.5, 784.8, and RB is 490.5. And mathematically, let me show you why this works. So what if the approach that we took was we just gave those variable names, the things that we don't know. So we said that for the row vector for the weight force, we had 0.5 for x, and we just called this some unknown a or something. Okay. And now take the cross product. You have 0.5 times this minus a times 0, it goes away. Okay. So this gives the same cross product as if we knew that. That's how this line of action thing works. And same thing for this. That row vector from the about point to where that boulder hits the wall. So we know the vertical distance is 0.8. We don't know the horizontal distance, so let's call that b, some unknown. So you have a b here. Now take the cross product, b times 0 minus that, and you get the same thing, whether it was there or not. Okay, so sometimes that's useful, and even if you know those values, thinking about it that way can sometimes just make the calculations a little quicker. Oh, one thing that's sort of interesting. Well, then it might not be quite as convenient, but you still have to go along that diagonal line. Yeah, it's pretty convenient in the case where it's horizontal or vertical. Yep.
Well, like, what if for some reason the gravity force was like negative 300
Uh-huh.
and then the
yeah.
row actually doesn't matter.
Yes, you're exactly right. I mean, we got to zero out components exactly because we had one vertical and one horizontal. So what you're saying is if this was at an angle, we couldn't choose the component to be 0 because it's going to act along this diagonal line, and we'd have to deal with that diagonal line. Yeah, you're exactly right. This is sort of a special piece that makes it simple. But you always can move it along line of action. It's just not always convenient, you know. Yeah, it just happens that we're talking about a horizontal force, so the line of action is horizontal, and a vertical force, so
it's just not hard to see how it is neutralized.
It's all in the cross product. Yep, that's right. One thing I was going to just point this out since I drew this picture. Well, I just mentioned that the weight force isn't really, when you're dealing with rigid bodies, you always treat the weight force like it's acting at the center of mass. So all of your mass is multiplied to g and acts at your center of mass. That's not really what happens. Really, there's just little bits of force everywhere. It's a distributed load. And so weird things like this happen. In a position like this, the center of mass would not be on this person's physical body. But the Epipolar system has all of his weight acting at this place at the top of his body. And that's, if you ever like watched high jumpers, they do that. They didn't always do this, but for the last 50 years or whatever, they run, they turn and go backwards over the bar. And the reason they use that technique is that if they're good at arching, they can arch, and at every instant their center of mass is well below where their back is. And if you like do the calculation at like every frame of a good high jumper's center of mass as they go over a bar, they'll get their entire body over the bar, not touch the bar, and their center of mass will never get as high as the bar. It'll go right underneath, a foot underneath the bar. Sort of cool. All right, so now we're going to get into three-dimensional rigid body statics. And I have to start by talking about three-dimensional joints. All right, so remember when I started talking about two-dimensional joints, I said, so remember, a 2D rigid body in space has 3 degrees of freedom. Has 3 degrees of freedom. Two translational and 1 rotational. And the number of variables that a joint introduced into Newton's laws all came from how many of these degrees of freedom it eliminates. Okay. So now let's think about a 3D rigid body in space. Okay, so I'm going to draw this sort of block thing. And I'm going to draw a bunch of axes. So there's one that way. There's one that way. And then one that way. Okay. And let's think about the degrees of freedom that this object has. Okay, well, the one that makes total sense, that's easy to imagine, is that now we have another axis of translation, right? You can translate along the positive and negative x-axis. You can translate along the positive and negative y-axis, just like you could in 2D. But now we have a three-dimensional space, so you can also translate along the positive or negative z-axis, right? So there's translation along 3 axes. But now think about the rotations. Before we only had 1 because you had to stay in the plane, but now you can rotate around that axis, and you can rotate around that axis, and you can rotate around that axis. Okay, so now you can have rotation around 3 different axes. And so altogether, this says that there's 6 total degrees of freedom. And the loads that are applied to a body by a joint, just like they were in 2D, are going to be determined by which of these degrees of freedom they eliminate. So each joint type eliminates, some set of these 6 degrees of freedom. Okay, so now I'm going to go through, just like I did before in 2D, I separated things into categories where a category introduced the same number of variables, the same number of loads. Again, the way it's going to work is if a translation is disallowed, it's going to be disallowed by a force along that axis. And if a rotation is disallowed, that's going to be done by a couple about that axis. Okay. Forces now are going to be given, a force vector is going to be shown like it was before, an arrow. But a couple vector is going to be shown by the direction of the vector, but the arrow is the arrow is going to have 2 heads on it. Okay. Okay, so I'm going to start with joint category 1. So these are the joints that apply a force with a known direction how many variables do you need to represent a force with a known direction? So for a force vector, if you didn't know the direction, you'd need all 3 components, right? If you do know the direction, though, you know a unit vector, and you can just think of that force as a number times a unit vector. So there's only 1 variable you need in this case. So to apply a force with a known direction, it brings 1 variable into the equations, into Newton's laws. And there are 2 of these that do that. The first one is a frictionless contact. So I'm not really going to try to draw this in 3-dimensionally, but it works the same way as it does in 2D. The direction is always perpendicular to the surface of contact. So if this is body 1 and this is body 2, then a free body diagram of body 1 make it look a little more like the one over here. Okay, is going to be perpendicular to this surface of contact. So it's going to be like that. So that's 90 degrees, and we call this, you know, N or whatever. Right. Yep. And the second type in 3D is a roller. So one thing, though, that you have to be careful with now in 3D is now we're talking about rollers that can move freely in any direction. Yes, question? The opposite. Yep, that's right. So a roller, but we're talking about like a ball roller, not a wheel. Because a wheel has a preferred direction. So in this case, we're talking about something like this. So if this is body one, again, free body diagram. If this is the surface, the force is a normal force perpendicular to the surface. Okay, so those are the two types of joints that bring one variable into Newton's laws. What about the directions? Could you get negative values for these ends, either of them or both of them? No, you could not, because a negative value of n would mean that the ground is like pulling down on it. Okay, so notice you have to get positive numbers for these. N must be positive for both of these. It could be 0, yeah. Yep.
So what's the difference between a ball roller and a frictionless contact?
There's no mathematical difference. It's just like, you know, if you're like in a, you're looking at a picture of a setup, or you're in a room looking at things, you just have to recognize that mathematically you treat them the same, you know. Okay, so now joint category 2. So there's only one of these, and I think actually there's only going to be one of everything from now on. And we're going to go all the way through all of these different numbers of variables that are introduced. What's the most number of variables that we're going to see? 6, exactly. 1 for each degree of freedom. So we're going to have a type for 2, 3, 4, 5, 6. So this applies force components in 2 directions. And introduces 2 variables into the equation. Into Newton's laws. And the only joint in this category is a wheel with a preferred direction. So that would look like this. Where the preferred direction is this way. Okay. And a free body diagram. If this is the direction that it's free to roll, what are the directions of the force that this applies? Well, it doesn't apply any force along the path that it can follow. It applies one perpendicular this way, and one perpendicular this way. So this is perpendicular, and this is perpendicular. So one of these is a normal force, and then this other one is like a friction force, or if it could be on a rail or something if it's like a a train. But something is applying a force that keeps it from leaving that path. Did I draw this right? That sort of looks like a MC Escher drawing, I think. Here's what we want. Any questions about that one? Right. Yep. Yeah, wheels we're always going to represent as frictionless. We'll talk a little bit about some kinds of wheel friction, I guess, right at the end. Okay, so now joint category 3. Well, it's frictionless along its path, but the friction keeps it on the path. Okay. I don't have a good demonstration of this. But... Okay, so now, what? What? Yeah, we'll be solving for F and N. Yep. So that's those are the two variables that it introduces. Joint category 3. Applies a force vector with a totally unknown direction. And so if you have a force vector with unknown direction, that means that it prevents translation anywhere, okay? So all translation is eliminated. We haven't had any couples yet, which means for all of these, rotation is possible around any axis. Okay, so this introduces 3 variables. And the joint in this category is a ball and socket joint. So you have one piece like that, one piece like that, and a free body diagram of that part 1. Has 3 force components. And you can just represent it as like the force on body 1 by body 2. If this is body 2. Okay, so here's a ball and socket joint. We have to pretend there's no friction, but there's a lot of friction. But let's think about the translations. Okay, so imagine this one's fixed. The thicker one is fixed. Is there any axis where I can translate the center of that ball out of that point? No, so all translation's fixed. So it makes sense that that there's a full force vector. But now let's think about the rotations. Okay, so let's just arbitrarily, let's say the x-axis is this way. Okay, can I rotate the top around an axis that way? Yeah, so that would be this. Okay, and let's say that the y-axis is this way. Can I rotate this around the y-axis? Yeah, that's like this. Okay. And then can I rotate it about the z-axis, which is like this? Yeah, that would be like, supposed to be able to. That'd be if I like grind it like that, you know? So that's why, so thinking about it that way, you can tell that there's a full force vector and no components of a couple. Okay. This is pretty much how like hip joints and shoulder joints work. Okay. Now here is the trickiest one to deal with. Joint category 4. So this is the trickiest one to use. You got to think about this one each time. And the reason is that you don't always treat it the same way. This introduces, well, let me say, it's up to, or it introduces up to, four variables into Newton's laws. And here's how it breaks down. There are 2 force components. And those are always there. And then there are 2 couple components. that are there only when not used as a coaxial pair. Okay, I just made up that phrase, but a pair that has the same axis. That sounds like an official thing. It's not. Okay, so let me show you how that works. So this is a pin joint without thrust. And it looks something like this. So you have one object here. Connected to another body here. And they're connected by a pin that goes through. Okay. You with me on this? And I'm going to call the axes, so we'll have one axis this way, one axis this way, so I'll call this X, this one's Y, that means this one's Z. I'll call this one body 1 and this one body 2. And let's think about the motions that are allowed here. So this one has the thing that I'm thinking of as member 1 is this really skinny piece on top, okay? And you can see the pin here is free to slide along its axis. So like that's the Z-axis in this picture. It's sliding along the Z-axis when it does this, okay? And let's think about translations and rotations. So if I position it like this, can this top piece translate along the x-axis, forward or back? No. Can it translate up or down along the y-axis? Not the y-axis, okay? But it can translate back and forth along the z-axis. So what directions are the two forces going to be applied? Yeah, so there's going to be one force in the x direction, one in the y direction. And now let's think about the rotations. Can this top piece rotate around the x-axis? Nope, that would be this, like, tipping this way or that way. Okay, I can't do that. Can it rotate about the y-axis? So that would be me twisting it like a screwdriver. No. Can it rotate about the z-axis? Yes, it can do that. That's the motion that it's kind of made for, you know. So a free body diagram of member 1 has a force component in the direction of x. So I'll call that the fx component. It has a force component that better not be gone. Oh. Okay. Free body diagram of member 1. Okay, so we got a force component along the x-axis. force component along the y-axis. And those two are perpendicular to each other. Wait, give me back the first one. Okay, free body. I'm going to try it one more time. Free body diagram of body 1. Okay, there's a force vector in the x direction. A force vector in the y direction. None in the z direction. These two are perpendicular to each other. And now what about the couples? Well, we said that there was a couple preventing it from rotating about x. So I'll call that a couple component mx. And there was a couple preventing it from rotating about y. So there'll be an my. Okay. When don't you need the couples? So when don't you use the two couples? So in a case like this, where you have two of these pin joints, you can think of these as hinges that share the same axis. Okay, so these are two pins, two pin joints with the same axis. Then think about the strength of like how of rotation about the axis. Okay, I guess we'll talk about this next Thursday. I think it's a sign from God. Yeah. Okay, so I'll do the rest of them next time. This is a lot anyways. The next one that's on the calendar, I don't, yeah, we'll just skip this one. Yep. Hi. Oh, let's see. What day is good for you?
I can, if you could schedule like some testing
Yeah.
center on Monday.
Sure, Monday. Will you send me an email just to remind me, and I'll have it there on Monday.
Okay, I'll set it.
Okay, perfect. Yeah.
Oh, yeah, I missed the test. I was out of town on
Yeah.
Tuesday.
Okay.
Is there,
Yeah, let's do it in the testing center. What day do you want to do it?
Monday would be fine for me.
Okay. You send me an email too, and I'll put it over there. Okay. Yep.
And then